Let us discuss the different types of energies which are important for this chapter. So, although there are many types of energies, for this chapter, work energy and power, we are going to discuss the two most important energies. One is the kinetic energy, and then we have the potential energy. The formula for kinetic energy is half mv square. It is represented by K. Potential energy is of two types. First, we are going to consider the gravitational potential energy, and then we have the elastic potential energy. Gravitational potential energy is the energy of an object because of its height. And the formula for that is m into g into h, where m is the mass, g is the acceleration due to gravity, and h is the height of the object. On the other hand, elastic potential energy comes into the picture when we have springs. So when a spring either compresses or it stretches, then we say that elastic potential energy is stored inside the spring. And what is the formula for that? Elastic potential energy is given by this formula, half kx squared. Now let us analyze each of the potential energies one by one, starting with gravitational potential energy. Now consider this image. We have an object apple which has been lifted up by a distance h. So initially the apple was on the ground. So we have labeled that by point A, and the topmost point is labeled B. So the distance between A and B is h. Now, in order to solve questions, it is very important for us to understand a concept called the reference line. Now, what does that mean? So let's read. A reference line is basically a point where the gravitational potential energy is assumed to be zero, and that's the reference line. So the ground in this case will be a zero potential energy. Hence, we can say that if the object were at A, which is on the ground, the potential energy for the apple on the ground would have been zero. After that, let's read this. Points above the reference line have positive potential energy. So over here, the point B is above the reference line. So potential energy will be positive mgh, which I have represented here. On the other hand, if you have points which are below the reference line, they have negative potential energy. So let's look at the same image. We have the apple, but under the ground or below the ground. In this case, the distance between A and C is h only, the same as above. So the magnitude of the potential energy will still stay the same, mgh, but it will have a negative sign. So potential energy of the apple at the point C will be equal to negative mgh. Now, why do we put a minus sign? Because the object is under the reference line. And while solving questions which deal with potential energy for this chapter, it is very important for us to analyze what is the reference line. So if we go above the reference line, potential energy will be positive. Below the reference line, potential energy will be negative. So this was all about the gravitational potential energy. The formula is mgh, but we need to be careful about the sign. Next off is elastic potential energy. We already know elastic potential energy will come into the picture if you have springs. If a spring either compresses or it stretches, then we say that the spring has stored elastic potential energy. So the formula for this is half kx square, where k is a constant dependent on the type of the spring. So k is the spring constant, and x, on the other hand, is compression or extension in the spring. So how much the spring has compressed or stretched, that is x. So imagine a situation if the spring is stretched a lot, so the value of x will be greater. So the spring would store a lot of elastic potential energy in that case. Now, just based on this formula, let's solve a quick question. So let's read. We have a spring in relaxed position which is extended by zero point 0.4 meters. The spring constant is given, and we need to find the elastic potential energy stored in the spring. So what is meant by relaxed position? So remember, relaxed position is the spring is neither stretched nor it is compressed. So it is in its natural length. Now, if you recall, the formula for spring force, let us write, is given by the Hooke's law, which is k into x. So if the value of x is 0, which means the spring is neither stretched nor it is compressed. So if the value of x is equal to 0, that is what we call as the relaxed position. So in that case, the spring force will be 0, and hence we say the spring is in the relaxed position, as no pulling or pushing force is being exerted on the spring. So that was the description of this word relaxed position. Now let's analyze. We have to figure out the elastic potential energy. So the formula is half kx square, right? So half kx square. Now the value of k, the spring constant, is already given 48, and the extension is also given 0.4. So that's it. Just put all the values in, and eventually we will get 3.84 joules. Hence, the elastic potential energy stored in the spring is positive 3.84 joules. All right, let's solve another question based on this logic of half kx square. Here we have a spring of spring constant 100 newtons per meter. It is compressed by 6 meters, as you can see in this diagram. A box is placed against the spring. At the point where the box has moved by 2 meters, how much elastic potential energy is stored in the spring? So we already know the formula for potential energy is half kx squared. So let's analyze this question properly. So consider this image on the bottom. Initially, the spring was compressed by 6 meters, as you can see in this image. In the second situation, the box has moved by 2 meters. So let me explain that. So consider this red line is the original position of the box in case 1. In case 2, the box has moved a little bit to the right hand side by 2 meters, as they have given in the question. Now the box has moved by 2 meters, which means there will be a change in the compression of the spring. And now we have to figure out the potential energy, which is half kx square. The value of k is already given to us as 100. So all we need to figure out is the extension or compression in the spring in the case 2. So initially in case number 1, we saw the spring was compressed by 6 meters. So initial compression is 6 meters. But what will be the final compression is case 2? Please do not assume 2 meters as the final compression in the spring, because if you analyze in the case 1, this 6 meter was the total compression. How do you find the compression or the value of x? We find the distance of the box from the relaxed position. So that is why initial compression in the spring was 6 meters. In case number 2, we have to figure out the distance of the box from the relaxed position. So this arrow is the final compression in the spring. So how do we figure that out? Total distance is 6 meters, out of which box has gone to the right 2 meters. So this will be 6 minus 2, which comes out as 4 meters. So we can write down the final compression in the spring is 6 minus 2, which is 4 meters. And that's it. Now we have all the parameters required. K is 100. The final compression is 4. And if we simplify this, we will get 800 joules as the elastic potential energy stored in the spring. Next, we have the total work done by the spring. So to find the work done by the spring, if you try to recall the most basic formula for work, which was Fs cos theta. Now try to think, can we even apply this formula to find the work done? The answer is no. And why is that? Let's read. We cannot apply this formula to find the work done by the spring since the value of F is not a constant. So let us try to recall. This formula of Fs cos theta is only applicable if all the parameters involved, like force, displacement, theta, everything should be constant. But in this case, if you remember the spring force formula, which is the Hooke's law, Fs is equal to Kx. So you can see the value of the spring force depends on x. So higher the compression or extension in the spring, more will be the spring force. So clearly the spring force is not constant. Hence, we cannot apply this formula. So if a question asks us to find what is the total work done by the spring, so we cannot apply this formula. So what do we do in that case? We have another formula which we need to remember. So work done by the spring is given by this formula. It is equal to negative of the change in elastic potential energy. On the other hand, if we have to figure out the work done on the spring, so the magnitude will still stay the same, but we will remove the negative sign. So work done on the spring is given by the formula positive change, delta is change of elastic potential energy. And the change in elastic potential energy, remember, is final minus initial. So we can write delta EPE is equal to the final elastic potential energy minus the initial elastic potential energy. And now we can summarize all the formula. Work done by the spring is given by the formula E initial minus E final. So why we have done initial minus final in this case? Because work done by the spring was equal to negative of the change in elastic potential energy. And because of the minus sign, we have written initial in the first place and final in the last. So while solving questions, be very careful. Is the question asking you to find work done by the spring or on the spring? So this was the formula for work done by the spring. In the case the question is find the work done on the spring, it is positive delta EPE, which will be just final minus initial. And now we can simplistically deduce that work done on the spring is equal to negative of work done by the spring. And now let us try to solve questions on springs. We have to figure out the work done because of the spring. So be careful in the question. You need to analyze, is the question asking you to find work done by the spring or on the spring? Depending on that, we will use the different formulas. So here we have a spring in the relaxed position extended by 0.4 meters. We have to figure out the work done by the spring. So we will start with the formula itself. Work done by the spring will be initial minus final, like we discussed earlier. And the formula for elastic potential energy we know is half kx square. Now, initially, the spring was in the relaxed position, which means we can write the value of x is equal to 0. So the spring is neither compressed nor it is stretched. So we can say that the initial elastic potential energy will be 0. Finally, the spring has been extended by 0.4 meters. So we can use the value of x as 0.4 meters. So here we go. Initial potential energy is 0 since the spring is in the relaxed position. Finally, we use half kx square, k is 48 and x is 0.4. And then we just subtract initial minus final. So we'll get 0 minus 3.84, which comes out as negative 3.84 joules. Hence, we can say work done by the spring will be negative 3.84 joules. Now, the same question we had done a while ago, where we found the elastic potential energy. There we found the elastic potential energy was positive 3.84 joules. So, if you analyze the work done by the spring and elastic potential energy stored in the spring are having different signs. One will be negative and the other one is positive. Here we have a spring that obeys the Hooke's law. It is stretched by a distance x and stores energy E. What is the work done by the spring when it returns to the point where x is reduced to half of its original value? Now, since we have to figure out the work done by the spring, we know the formula is initial energy minus the final energy. And the formula for elastic potential energy we know is half kx square. So initially they have given the energy is E. So let's write it down. Initially the energy is E, the distance, the stretching distance is x. So we write down half kx square. In the final situation, x reduces to half of its original value. So final energy, let us write EF, that will be equal to half k. The value of x will be x by 2 squared. Now, if we simplify this, we'll get half kx square and then we'll have a 4 in the denominator. Now, half kx square is nothing but E. So, the final energy we can write is E upon 4. Now, according to the formula for work done by the spring, we have to subtract both energies, keeping initial in the first place. So, let us write the work done by the spring will be equal to the initial energy, which is E, minus the final energy, which is E by 4. And if we simplify this, we will get 3E by 4 as our answer, which means option C is correct for this question. Okay, this is a graph-based question. We have been given a graph. X-axis is the force and the y-axis is displacement. The elastic potential energy stored in the spring is E when the extension is E. We have to figure out the work done by the force on the spring to increase the extension to 3E. So step number 1, please identify, do we have to find the work done on the spring or by the spring? So let's see. We have to figure out the work done but on the spring. So let me underline this, work done on the spring. Accordingly, our formula will change. So work done on the spring, we'll write final energy minus initial energy, where the energy is half kx square. Now, initially it is mentioned that the energy is E. So let us write it down. E will be equal to half kx square, but in this case, x is E since the extension is E. So we will write half k E square. Finally, let us write down EF. Let's say EF stands for the final elastic potential energy. So we will write half k and the new extension is 3E. So in the brackets, we will write 3E whole squared. So this comes out as half ke square and we have a 3 square which is 9. Since half ke square is equal to E, which means we can write the final energy can be written as 9E. Now let us apply the formula final energy minus initial energy. So we'll write 9E minus E. So let's write down. Work done by the spring will be 9E minus E, which comes out as 8E. And hence, option C is the right answer for this question. Next, here we have a spring of K value 200. It is compressed by 6 centimeters. At the point where the box has moved 4 centimeters, how much work has done by the spring? So like always, we have to figure out the right expression for the work done. Since the work done, we have to find by the spring. Hence, the formula will be initial energy minus final energy. So let's solve. So consider this as case 1 when the box is in this position and the spring has been compressed by 6 centimeters. Case 2, when the box has moved by certain distance. So analyze this. Let's say this red line represents the position of the box in case 1 and this red line represents the box in the case 2. So it is mentioned in the question that the box has moved to the right hand side by 4 centimeters as I have shown here. So we can say that like in case 1, you can see the compression in the spring is 6 centimeters. So initial compression is 6. But what will be the final compression? If you recall, compression is the distance of the box from the relaxed position. That's why we said initial compression was 6 centimeters. In case 2, when the box has moved some distance, so the distance of the box from the relaxed position, this arrow will represent the final compression. So that will be 6 minus 4, which will give us 2 centimeters as the final compression in the spring. Now the work done by the spring, the formula is initial energy minus final energy. Initial energy will be half kx squared, and let's put all the values in. The value for k as given in the question was 200 and the value of compression 6 centimeters. So we convert that into meters first. And if we solve this, we will get 0.36 joules as the initial elastic potential energy stored in the spring. Finally, the formula stays the same, but the only difference is the value of x. The final compression in the spring was 2 centimeters. So if we convert that into meters and use it, we will get 0.04 joules as the answer. After finding out these two energies, we use the expression work done by the spring will be initial minus final. So it will become 0.36 minus 0.04, which comes out as 0.32 joules. So coming back to the question, option C is the right answer for this question. Here it is mentioned that an object of mass 0.78 kilograms attached to a spring of unstretched length 560 millimeters. So let's draw a diagram. So watch. We have a vertical spring of unstretched length 560 millimeters. This means 560 millimeters is the natural length of the spring, where we can say the spring is neither compressed nor it is stretched. Hence, we can say that the force on the spring in this position will be equal to 0. So this is the relaxed position of the spring. Now analyze. If we put a box of mass 0.78 kilograms and attach it to the spring is of course going to extend. And the new length of the spring is given as 620 millimeters. So let's analyze this in a diagram. So here we have the box of mass 0.78 kilograms. Because of the weight of the object, the spring has been extended and the new length of the spring is 620 millimeters. Now we have to figure out the total energy stored in the spring as a result of this extension. So the formula for energy, elastic potential energy, is given by half kx squared. First of all, the value of k is not given here. So we need to do something to figure out the value of k. And also we need the final extension in the spring. So how do we figure that out? Let's analyze. So in case 2, when the box was kept, the total length of the spring was 620 meters. And initially, the length was 560 meters. Hence, we can say if we subtract these two lengths, that will give us the total extension in the spring. Hence, we can write extension x will be equal to 620 minus 560, which comes out as 60 millimeters, which can be converted into meters like this, because while using the formula, we have to take the value of x in SI units. So x we have found. Now the value of k, the spring constant, is clearly not given. So how do we figure that out? For that, we have to use this information. It is saying when the object has come to rest. From this information, we can deduce that if the object is at rest, then the net force acting on the object will be equal to zero. Next step would be to identify what are the different forces acting on this object. The first is, of course, the weight of the object, which is mg acting downwards. And then we have a spring force. Now, the spring force is either pulling or pushing, depending on whether the spring has been extended or compressed. So, in this case, the spring has clearly been extended. So, the spring is going to pull the object upwards. So, let's analyze this. So, we will represent the Fs is the spring force pointing upwards. Now, since we have deduced that the net force on this object will be zero, hence the spring force and mg will have to balance each other out. So, let's write Fs will be equal to the weight of the object. Spring force by Hooke's law is kx, which will be equal to mg. Now, if we make k as the subject and try to put all the values in, the value of x, the extension we had figured out was 0.06, mass is given as 0.78, and the value of g is 9.8. Now, if we simplify this, we will get the value of k as 127.4 newtons per meter. Now, we have the values of both parameters, k as well as x. So let's write down the formula half kx square, and the value will be half. K is 127.4, x is 0.06, and finally we get 0.23 joules is the energy stored in the spring because of this object. And this is how we solve questions of this type. Please remember the formula half kx square, but it is important for us to identify the correct extension value. And how do you find the value of k? By balancing the spring force with mg, because earlier it was given that the object had come to rest. Springs in series and parallel, so we are going to consider them one by one. What is series kind of arrangement? So if there are multiple springs connected to one another, like this orientation, one after the another, this is called a series type of arrangement for springs. Now, in the exam questions, we might have to deal with certain cases where springs are attached like this. So this is a series arrangement. According to the Hooke's law, F is equal to kx. So there are three important parameters which are dealing with here. Fs stands for the spring force, k is the spring constant, and x is the displacement, which is just how much the spring has been extended or compressed. So for a series arrangement setup, please remember spring force in springs is the same. And why do we assume that? Now, since this is a single string, that is why the total force in this entire string will be the same. This is similar to the concept of tension. If you remember, tension in a rope will stay the same as long as it is one single rope. A similar reasoning works here. So the springs are connected one after another in a straight line. So the spring forces in both the springs will be the same, whereas the extension in the springs will be different. So how much extension happens in a particular spring depends on the value of k. So if you have a heavier spring, that will extend lesser. If a spring is lighter, let's say the value of k is lesser, that will be able to extend a lot more. So to sum up, in series, Fs stays the same, but extension x is different. On the other hand, how does a parallel spring arrangement look like? So if the springs are connected in this fashion, so you can see both the springs are connected to the box. This is called a parallel type of arrangement. Now, there are various types of parallel arrangements which you might encounter in the question. So one is this type, case A. Case B is the vertical orientation of the same. So two springs connected to the same box, but they are vertical. Case C, so the box is connected to both the springs, but one of the spring is connected to one wall, another spring is connected to the another wall. So like in series arrangement, we'll do the same analysis, but the analysis will be reversed. In series, the spring force was the same, extension x was different. In parallel, the reverse will happen. So let's write, in a parallel arrangement, the spring force in the springs will be different, but the extension in the springs will be the same. So like you can see in this image, if there is a box connected to two springs connected in parallel, if we try to push the box to the right hand side, so you can see both the springs are going to be extended by the same amount x. And that is why we say in a parallel arrangement, extension is the same, but the spring force will be different. Because remember, the spring force is k into x. So if x is constant for parallel, the spring force will be directly proportional to k. So stronger the spring, which means higher the value of k, more will be the value of spring force, and vice versa. Now, how do we solve questions which involve springs either in series or parallel? There is a concept called equivalent spring constant. Let's discuss that one by one in series and parallel. So a series arrangement looks like this, where the two springs are connected one after another like this. So in this case, we can replace both springs with one spring. That will be the equivalent spring constant. And how do we find that out? There is a formula. So the reciprocal of K equivalent, 1 upon K equivalent, will be equal to 1 upon K1 plus 1 upon K2. This formula we are going to use to solve questions. Whereas in case of parallel arrangement, this is the orientations. So even in this, you can see there are multiple springs out here. So we can replace both springs with just one spring called the equivalent spring constant. But in case of parallel, the formula is different. So the equivalent spring constant is just the sum of K1 and K2. So depending on the type of orientation, whether it is series or parallel, we have to use the different formulas to find the equivalent spring constant. And let's summarize what we have learned so far. Springs in series and in parallel. For a series setup, the spring force is the same, but the extension is different. And this is the formula. For a parallel arrangement, the reverse will happen. So the spring force is different for both the springs, and extension in the spring will be the same. And the formula is just the addition of the two spring constants. So here we have a system that consists of two identical springs connected in series, and the total elastic potential energy is EP when a load is added to both the springs. This is case 1. In case 2, one of the springs is removed and the same load is attached, and we have to figure out the total energy stored in the spring in case number 2. How do we do that? We start with the basic formula for elastic potential energy, which is half into K into x square. Now, in case number 1, where the springs are connected in series, the easiest way to approach such questions is to use the concept of equivalent spring constant, which means even though there are two springs, we can remove them and just put one spring having a spring constant which is called as equivalent spring constant. So the formula for equivalent spring constant in case of series is this. Now, since the springs are identical, let's say the springs are having spring constants K each, since the springs are identical. And now let us write down the formula. We will write down 1 by K equivalent will be equal to 1 upon K plus 1 upon K, which is equal to 2 upon K. And if we take the reciprocal, the equivalent spring constant will come out as K by 2, which means instead of two springs, we can attach just one spring. So let us draw. This is the same situation, case number 1. We are removing both the springs but connecting one spring, which is having a spring constant of K by 2. And then there is a block of, let's say, mass M attached to it. Now, in the question, it was mentioned that the total energy stored is EP. So let's write down the EP will be equal to, now the formula for potential energy is half kx square. But we have figured out the equivalent spring constant is K by 2. So we will write down half into K by 2 multiplied by x square. Now, let's say in case number 1, the extension in the spring is, let's say, x1. So even in the formula, we will write x1. Now, at this stage, since the block is connected to the spring and the block is at rest, we will write that the net force acting on the object is equal to 0. Since it is not moving up and down, it is at rest, so the net force will be 0. After this, let us try to figure out what are the total forces acting on this block. So the first is the weight of the object itself, which is mg acting downwards. And then we have the spring force, which is acting upwards. Why is it acting upwards? Because the spring has been stretched. That is why the spring will try to pull the block up. So spring force and the weight of the object should balance each other. So let's write down Fs will be equal to mg, and the spring force is given by the Hooke's law, which we will write as K by 2 is the spring constant multiplied by x1 is the extension. So this is equal to mg. Now let us make x1 as the subject. So we will write 2 mg by k. And at this stage, let us put the value of x1 in the elastic potential energy expression. So let us write EP will be equal to half multiplied by K by 2 multiplied by 2 mg upon K whole squared. Now, if we simplify this, let's see what do we get. The EP we will come out as m square g square divided by k. Since the 4 will get cancelled out with this 2 square, So this is the total potential energy stored in the springs in case 1. In case 2, one of the springs has been removed, but this spring is also having the same spring constant of K. So now we will do the exact same analysis, but for case number 2, where only one spring is connected. So in this case, let's say the potential energy is EP dash, which we have to figure out. So that will be half K into X squared. In this case, let us assume X2 is the total extension of the spring in case 2. Over here, we apply the same logic that the net force acting on the load or the object is equal to 0, which means the downward weight, which is mg, that has to equate the upward spring force. So let us write down the spring force will be equal to mg, like we did in case 1. Spring force will be K multiplied by x2 according to the Hooke's law, and the weight is the same mg. If I make x2 as the subject, we will write mg upon k. And now we will put this value of x2 in the expression for EP dash. So let's write EP dash will be equal to half multiplied by k multiplied by mg divided by k whole square. And now let's simplify this. The final potential energy in case 2 we will write as m square g square upon 2k. Now all we need to do is just compare the final potential energy with the initial potential energy, which was m square g square upon k. So m square g square upon k is EP. So over here in the expression, what we can do, we can replace the m square g square upon k with EP, which was the original potential energy. Hence, we can write EP dash comes out as EP divided by 2, which means when the spring, one of the springs was removed, the total elastic potential energy also got halved. Now, going back to the options, let's see which is the right answer. So, in option C, we can see a zero point 0.5 times EP, which is nothing but EP by 2. And that is why C is the right answer for this question.